All right, everybody, number 18 and 4.6, they're asking you to do everything here, guys. Find the transition points, intervals of increasing and decreasing, concavity, asymptotic behavior, although we're not going to deal much with that here, and then sketch the graph. So basically, the end result here is the graph that we're going for in number 18. So let's dive into it. Now, by the way, I just mentioned asymptotic behavior. We are dealing with a cubic function here, guys, a polynomial. We're not going to have any vertical or horizontal asymptotes to worry about. So let's find our I wanted that to be blue, darn it. All right, let's go to our first derivative now. I'm going to get lazy and call that y prime. And what's that going to do for us? 3 times 1/3 is 1x squared plus a 2x and a plus 3. That derivative will never be undefined, but I do think it's going to equal 0 at a time. Tell you what, guys, I'm feeling ambitious right here. I think that if I were to just maybe smoosh all this over a little bit like so, and then draw a black line right down the middle of this problem, I might be able to do my first derivative and my second derivative kind of simultaneously. So let's see how this goes. I might regret that. All right, back to the first one here. Setting it equal to 0, we want to try to solve that by factoring, and I am pretty... Oh, wait a minute. I think we ran into a problem right off the bat. I copied that down right, didn't I? Plus and plus. Okay, gotcha. If this had been a minus 3 right here, guys, this thing would have factored into x plus 3 and x minus 1, but that does not happen right here. As it is, there are no two real numbers that multiply to 3 and add up to 2. Well, that's just kind of a kick in the gut right to start off right here. So I thought that one was going to go fast. All right, guys, so we're a little bit stuck right there. What are we going to do instead? When all else fails, you can use the quadratic formula or completing the square. I would think most of you guys would probably want to use your calculator in order to solve that. I actually prefer completing the square here because a is 1 and b is even. So it's x squared plus 2x equals -3. You take half of b, which is 1, square it, 1, and add that on both sides. Plus 1 plus 1. Ah, okay. And we get x plus 1 quantity squared, this is interesting, is equal to -2. Square root on both sides, and I can stop right here. I end up with x plus 1 equals, and the square root of a negative is going to be imaginary. And we're not dealing with imaginary numbers here, guys. We're trying to graph this function on the real coordinate plane here. So what that tells me is there are no real critical values. No values of x are going to make this derivative here either 0 or undefined. So what does that do for us then, guys? Usually, I would do a bunch of work right here. I'm going to delete that real quick. And usually you'd come up with something, like x equals 3, okay? And you'd put a box there and you'd make a chart, and here you'd guess x equals 2, and here you'd guess x equals 4, and you'd find out what's going on. But since that doesn't happen here, guys, that means right now, if there are no critical points, there are no local max or min values right here, and this whole function is either going to be increasing or decreasing. So at this point, you could choose any x value that you wanted right here. For example, we could choose x equals, let me go with that 3 that I had just a second ago. And what you would find there is that y prime of 3 is 9 plus 6 is 15 plus 3 is 18. It's positive, and that means that the original function y is increasing. On what interval? For all real numbers. What we're dealing with here, guys, your second derivative is a parabola that opens upward that never touches the x-axis. It looks like this. And if that's the graph of y prime, that means your derivative is always positive, so your original function always increases. That's kind of a weird one. We haven't gone over anything like that, at least together as a class, this year. Okay, so what I know then, guys, is that this graph, in fact, let me just say here that y increases on the interval from -infinity all the way to positive infinity. And if I think about what a cubic function can look like, most of us want to think that a cubic function with a positive leading coefficient is going to do something that looks like this, which increases, then decreases, then increases again. But the kicker here, and I've tried to mention this in class a few times, without a negative x term anywhere here, I don't think there's any reason to think that this function is going to take a dip backwards. I think it's very possible here that this cubic function basically does something like that, which would support this idea right here, that this function, which we're just calling y, increases for all real numbers, and it never decreases. Kind of interesting. Okay, well, let me get rid of this graph because I'm getting ahead of myself right now. That's what I've learned from the first derivative. Now, however, let's see what the second derivative tells us. And I think this is going to be both more interesting, but also more traditional with what we're used to seeing. The derivative of our derivative, guys, is going to be a 2x plus 2. We'll set that equal to 0. Of course, that'll never be undefined. And we'll get x equals negative 1. Right? Right. So now, there you go. We have a potential point of inflection here. So I'll make a table. I'll choose an x value less than negative 1, like negative 2, and greater than negative 1, like 0, and we'll put these values back into the second derivative. So y double prime of negative 2. 2 times negative 2 is negative 4 plus 2, that's negative. We are concave down on that interval for all x values less than negative 1. But when we plug 0 into the second derivative, 2 times 0 is 0 plus 2 is positive, we are now concave up. So what have we found, guys? This is a point of inflection right here. So we have a point of inflection at x equals negative 1, and we know that we are concave upwards for all x values less than negative 1. I'm sorry, that is all x values greater, I was doing that backwards there, greater than negative 1, and we are concave downward for all x values less than negative 1. So I did learn 3 things here from the second derivative, and really, the only interesting thing I learned from the first derivative is that this function is always increasing. Now, in previous sections here, when they've asked you to find a point of inflection, it's always just been an x value. But since we're actually graphing this thing right now, guys, it would probably benefit us to go ahead and find the y value where that point of inflection occurs, and that's going to happen by putting that negative 1 value back into the original function up here at the top, which unfortunately is going to get just a little ugly for us because of this fraction here. 1/3 times negative 1 cubed, that's a negative 1/3. And then plus negative 1 squared, that's plus 1. And then a minus 3 at the end of all that. So that's a negative 2 minus another 1/3 right there would be negative 2 and 1/3. Now that is really, you guys, all we have to go on here to come up with the graph of this function. So I'm going to try to do this a little bit more formally right here. But boy, there really isn't a whole lot going on here. Negative 1 on my x-axis, and then I'm going to go down to negative 3 on my y-axis. And all I know is that my point of inflection is roughly right about there. So what do I know? Prior to that 1 point that we came up with, the function has to be increasing, and on the left, it has to be concave down. So I'm going to draw a graph. Let me zoom out just a little bit here, guys. I'm going to draw a graph that is increasing and concave down, although I find it a little easier to draw this way. That, I think, is what this graph is going to look like here at that point. And then after it hits that point of inflection, the graph continues to increase, except now we're concave upward. So I think that graph is now going to look something like this. And by the way, I cheated right there. I went back up before I didn't stop at all. There is no c value. There's a plus 0 here. That would be our y-intercept right there, guys. So I kind of knew that that graph was supposed to pass through the origin. Guys, that's what this graph is going to look like. Now, before I started recording this, I went ahead to my Inspire and I defined that function in there because I thought I was going to need it to come up with some values, just to make sure I got this right. We did f1 of negative 1, if I'm not mistaken, and we got negative 2 and 1/3. Yeah, that's negative 7/3, so we did that right. But if we just wanted to make sure we were good, I could add a graph page here real quick, hit my up arrow, and there's f1 of x, and hit enter. And sure enough, that's about what our graph looked like. Your calculator will do some cool things, you guys. One of the things it will do is if I go to my menu button now and then go to Analyze Graph, it'll find a point of inflection for us. So right about there. So for lower bound, you guys are just going to use your left and right arrows to get this point somewhere to the left of where you think that point of inflection is, and you'd hit Enter. And then your right arrow would move over here, and you'd hit Enter as well. And sure enough, there's our inflection point at -1, and then that would be -2 1/3, which I believe is exactly, wait for it, there it is, -1, -2 1/3. And everything else we saw on that graph supports what we came up with right here. Okay, guys, that is everything they asked us to do on problem number 18, so that one is all set now.